Integration by substitution. In the previous video, we found the primitives of the most common functions using formulas and simple rules, but for more complicated ones, we have to use some techniques for integration. Now we discuss a simple but essential technique, the substitution method. Thanks in advance for watching this video. If you like this video, don't forget to like and subscribe to the channel and activate the bell. It's very important for the continuity of this channel. There are occasions we will want to evaluate an integral that involves a composite function in such a situation by using substitution or a change of variables. The function simplifies, and then the basic formulas of integration can be used to integrate the function. The purpose of using the substitution technique is to rewrite the integration problem in terms of the new variable, so that one or more of the basic integration formulas can then be applied. We introduce the technique through some simple examples for which a linear substitution is appropriate. Let's see how it works. Calculate the indefinite integrals. We can find the integral of item E directly, as the integrand is complicated due to the presence of the term x plus 1. We can consider this as a composite function, where the integrand has an outside function g of t equals t to the power of 3, and an inside function f of x equals x plus 1. So we make the substitution t equals x plus 1. We must take care to substitute appropriately for the term dx as well. So we take the derivative of t with respect to x and solve for dx. In this example, because t equals x plus 1, it follows immediately that dt dx equals 1. So dt equals dx. We substitute t for x plus 1 and dt for dx. We rewrite the integral in terms of t and proceed as follows. After this substitution, we are left with a basic function, so we can find its primitive directly. We can convert to an expression involving the original variable x by substituting x plus 1 back in for t. Don't forget that the purpose of using the substitution technique is to make an appropriate substitution to reduce the given integral to a known form of integration. So think about what substitutions make the following integrals easier to solve. Item B, we make the substitution t equals 5 times x, because we know the integral of the sine function. Item C, we replace 2 times x with t. And in item D, we replace 5 times x plus 3 with t. In item E, we replace 1 minus 3 times x with t. The next step is taking the derivative of t with respect to x and solving for dx. We now rewrite the integrals in terms of t and dt. In other words, this means that all terms involving x and dx must be transformed into terms involving t and dt. The resulting integrals can be evaluated immediately with respect to t. Replace t with the expression involving the original variable x to write the result in terms of x only. Basically, we make the substitution in order to simplify the integrand so that the integration process is easier. But the choice of a substitution that simplifies the integrand is not always easy. Before continuing, let us state the general form of integration by substitution. To integrate a composite function f of t that involves the derivative of the inside function t, write the integrand in the form f of t times dt by dx, incorporating constant factors as required in f of t. Then apply the formula or use a slightly different notation. In general, we need to look at the integrand as a function of some expression, which we will later identify with t, multiplied by the derivative of that expression. In short, we make a substitution for a function whose derivative is also present in the integrand. The next example makes the substitution rule clearer. We can see that 3 times x squared is the derivative of the function x cubed plus 1. So we make t equal x cubed plus 1 and take its derivative. And then we proceed as in the previous examples. We observe that the factor 5 times x is, apart from a factor of 2, the derivative of x squared. We substitute t equals 9 minus x squared. So dt dx is minus 2 times x. And then we proceed as in the previous examples. We make the substitution t equals minus x squared because its derivative, apart from the constant factor minus 2, occurs in the integral. Thus, we apply the substitution rule as follows. Sometimes the substitution is hard to see until we make some algebraic calculation to find out the correct substitution. It takes practice, and more practice. Take a look at the next examples. This example is a little bit different from the previous ones because it makes sense to let t equals x plus 3. But the derivative of t does not appear as a factor in the integrand. So let's continue with the substitution anyway. If the first guess doesn't work, we will try another substitution. Making the substitution, the integral becomes. This is a problem because our integrals can have a mixture of two variables in them. Usually, this means we chose our t incorrectly. However, in this case, we can eliminate the remaining x from our integral by using. We now can perform the integration. In this example, let t equal the denominator expression, and the derivative of t is 2 times the exponential. So let's continue with the substitution. Well, as we can see, we get a big mess because we have a mixture of two variables in the integrand, and there is no way to avoid it. We cannot eliminate the remaining x from our integral. This means we chose our t incorrectly. We will try another substitution. We rewrite the integral as follows. We make the substitution t equal to the natural exponential function only. We now can eliminate the remaining x from our integral and perform the integration. Pay attention. Sometimes an apparently sensible substitution does not lead to an integral you will be able to evaluate. You must then be prepared to try out another substitution. The ability to carry out integration by substitution is a skill that develops with practice and experience.